Okay. Last class we have been discussing this autoregressive modeling, and then we gave you the equations whose solution give rise to the AR parameters. Also, we derived what is called that linear prediction lattice. Okay. Just few things, a little more things about this AR modeling will be considered today. First, that is, suppose you have got a white process UN. I called it EN last time, but maybe I change it to EN. Say EN okay. This is XN. We are considering either AR modeling or linear prediction problem. In any case, we have got this equation. Say a pth order problem into En. If it is a linear prediction problem, En is orthogonal to the past p samples, that is xn minus 1, xn minus 2 up to xn minus p. If it is an AR modeling problem, En is a white sequence and is orthogonal to all the past of x. Okay. In the case of linear prediction, En is not a white sequence. En is orthogonal only to xn minus 1 up to xn minus p. Okay. In general, it is not an orthogonal sequence. In any case, En will be a sequence. So, you can model this even in the case of linear prediction. You can model this by a filter like this, that okay, there is a linear prediction error sequence called En. Okay, may not be white, and white in the case of AR process. It is passing through a model AZ. What is AZ? That is the transfer function of this AR system and gives rise to Xn. What is AZ? AZ is Xz by Ez. If you take Z transform left hand side and right hand side, obviously you get that all pole transfer function, and that is your AZ. Okay. If you want, you can put a constant here also, but I absorb that in En. Okay. So, this is that model. We showed methods by which you can estimate A1 to AP, that is, you solve the Wiener equations. Ideally, if you put the actual correlation values, then you get the actual solutions, but of course, you do not get the actual correlation values. So, you have to use the sample average based estimates of those correlation values, and you get this. Okay. Once you know them, you consider A e to the power j omega, that is replace Z by e to the power j omega, you get the transfer function, there is a DTFT. Okay. Mod square of that times some constant will be the output spectral density. That constant is the input variance, that also comes out of a solution for solution of the Wiener equation that you have seen. Now, point is, you are getting some solution from the Wiener equation, and I am now considering the ideal case where you have really put the ideal actual correlation values in that matrix. Question is, the solution that you get from A1 to AP, does it give rise to a stable and causal filter for AZ? That is, does it give rise to poles, a system that has poles, that is roots of this denominator polynomial lying within unit circle? Answer is yes. Wiener equation guarantees that, and that is what we will prove now. And again, there are various ways of proving it. I will follow a simple way, okay, which is easily appreciable. I read it in a paper by P.P. Vaidyanathan, and he obtained this proof while just teaching in a class, and I like that proof very much. I will follow that. So, we will show that all roots of this denominator polynomial, they lie within unit circle. Any polynomial whose roots lie within unit circle is called a minimum phase polynomial. Okay. For that, what I do, given AZ, I factorize it. AZ, what is the order of AZ? P. So, there will be P first order factors. Okay. The poles can be, the roots can be complex, I agree, but they are all first order factors. Now, out of that, take out say one particular factor that has a root at say q. So, our style is to write like this q z inverse. So, at z equal to q this is 0 obviously 1 minus 1 and remaining is c z. C z, what is c z? C z will be of degree what? P minus 1, this is very important. So, it could be something like this C 0 plus C 1 Z inverse plus dot 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 plus C P minus 1. So, that means the model can be written like this C Z followed by 1 minus Q Z inverse. Here is your E n. You can call this intermediate signal as y n, output is x n. Okay. Obviously, x n is what? If you see this differential equation, this transfer function 1 minus q z inverse means in time domain 1 minus, that is what does it mean? Y n minus q y n minus 1. So, x n is equal to y n minus q, z inverse amounts to a delay operator, delay operation by one cycle. So, q into y n minus 1. Now, we know or maybe sorry, I just missed out something. Actually, this is not A z, just A z was this A prime z. A prime z was the denominator polynomial. This is your x z by E z. Our purpose is to show that A prime z has all its roots within unit circle. So, now look at this equation. This is a slight change from what I drew just a while back. That means x z into A prime z is equal to E z. So, that means if you have an A prime z, we write like this. We take out one factor out into C z. C z we have already given the expression, so no point in writing. So, A prime z into x z, that is E z. So, if you have a system that whose input is x n and then followed by C z followed by 1 minus q z inverse and that is your E n. Obviously, x z into A prime z together is one A prime z. So, x z into A prime z is E z. So, I am just breaking A prime z as a factor cascade of two systems, one is C z, another is 1 minus q z inverse. So, output will be E n, intermediate variable is y n. So, by the same logic E n is y n minus q y n minus 1. Now, we know E n is orthogonal to x n minus 1 to x n minus p. Okay. Now, what is y n? Y n is C 0 x n plus C 1 dot dot dot. Total term is degree of C z is p minus 1, not p. This is very important. Degree of C z is p minus 1 and not p. So, it will go up to p minus 1 x n minus p plus 1. So, what is y n minus 1? Instead of n, put n minus 1. Okay. So, you see y n minus 1 consists of what? The past p samples of x n, that is x n minus 1 up to x n minus p. Therefore, E n is orthogonal to y n minus 1, because E n is orthogonal to x n minus 1 up to x n minus p. So, E n is orthogonal to y n minus 1, that is correlation between E n and y n minus 1 is 0. If that be the case, that means in that case what I can write, what I can do is, I know that E E n y star. See, it is important I told you that y n consists of, C z is a polynomial of degree p minus 1. That is why when you consider y n minus 1, you start at index n minus 1 for x, but go only up to n minus p, not any term beyond that. because that extra term, if you go one step further in the past, say x n minus p minus 1, that may not be orthogonal with E n. Okay. We have got strictly terms from x n minus 1 to x n minus p, and that set is orthogonal to E n, and therefore, E n is orthogonal to n minus 1, and that is 0. If you now replace E n by this expression y n minus q y n minus 1, what you get is, that is replace E n by, replace this by what I wrote earlier, y n minus q. So, if you substitute, what you get, r y y. Now, since there are several processes involved, let me bring in the subscript. So, r y y 1 minus q r y y 0, that is equal to 0. So, q r y y 0, r y 0 is E of mod y n square or E of mod y n minus 1 square. Okay, so, this is, of course, we are considering WSS processes, that is very much there. So, this is one relation we find. Next is, we also know that since we are not considering a non-deterministic process, x n cannot be given by a linear combination of its past, and therefore, inversely E n cannot be given by a linear combination of the past values of x n. So, that means this is strictly greater than 0. E n cannot be 0 random variable, because E n is 0 random variable, that means x n is exactly given as a linear combination of past p samples. That is not a deterministic, that is not a non-deterministic process then, but we are considering purely non-deterministic processes. So, that means E n cannot be a 0 process, E n cannot be a 0 random variable, which means variance of E n has to be strictly greater than 0. But this means E of what? E n into E star n. And what is E star n? E star n is, you replace again y n minus q star, this is greater than 0. Consider the second term is E n into y n minus 1 star, that is 0 because E n is orthogonal to y n minus 1 that we have seen earlier. So, forget that term. So, what you get is, this leads to E of E n y star n greater than 0. Okay. This means, now if you replace E n again by y n minus q y n minus 1 and carry out the sum, what you get, r y y, that is E n again is replaced by this expression y of n minus y of q into y n minus 1, q into y n minus 1. Okay. If you do that, what do you get here? R y y 0 minus q just a minute. It will be better if I consider it in a different way, slightly different way, then the proof will be easier. That is, we know the philosophy E of mod E n square greater than 0 this to the fact E of E star n E n greater than 0. Maybe here you replaced. Here you replace by E n by y n minus q. This makes it simpler, y n minus 1. So, y star n, another term is, the second term is y n minus 1 star E n, that is related to the correlation between E n and y n minus 1, just the conjugate of that. So, that is 0. E of E n y star n minus 1 equal to 0 means E of E star n y n minus 1, that is also 0, conjugate, just conjugate. So, the second term amounts to that. And first term is y star n E n. Okay. And then you replace E n by this expression y n minus q y n minus 1, then what do you get? If you replace, actually I need some space. Q y n minus 1 E n, that term becomes 0 and you are left with E of y star n E n greater than 0. What is y star n? What is E n? E n again you replace by this. So, what you will get is R y y 0 minus q star 1 greater than 0. Okay. Easy. E n is replaced by this y n minus q y n minus 1. First term is y n into y star n. This R y y 0, it will give rise to. Second term q comes out and y star n y n minus 1, that is R y y star n, you can easily see now. And for the first equation we can put R y y 1 equal to q R y y 0. So, this means actually if you replace R y y 1 equal to q R y y 0, what is R y y star 1, that is q star R y y 0. R y y 0 is real, it is variable, so it cannot be star. So, only it becomes q star into R y y 0. So, if you bring that here, what do you get? R y y 0 into within bracket 1 minus mod q square. This is greater than 0. Now, R y y 0, as I told you, this is this quantity. No, sorry, this is not. R y y 0 cannot be 0, because what is y n cannot be a 0 random variable, because that means what is y n after all? Y n is a linear combination of the past values of x. I mean x n and so p minus 1 past values. If that is equal to 0, that means current sample can be again expressed as a linear combination of past p minus 1 values, which is not the case for non-deterministic process. So, this is greater than 0. That means what you have here, what we have here is 1 minus mod q square, that is mod q should be greater than 1. Sorry, mod q should be less than 1, which means the root is within unit circle. So, this I separate out, this I did only for one root, I took out one root. So, took out that factor 1 minus q z inverse separately, and rest of them I put under another polynomial c z. Now, I can go on doing it to each and every root. This only proves that every root of that polynomial is within unit circle. So, provided you provide accurate estimates of the autocorrelation values in the Dullocker equation, you get this. Okay. So, it guarantees the stability and causality of the AR model. So, that is all for AR modeling. I now consider another application of this random process theory, that is called Wiener filtering or linear mean square estimation. Here for simplicity, I will consider only the real case, real valued signal, and then I will give you the result for complex valued case, but I will not derive them. Here the again I will be considering only FIR filtering, not IIR, because that is more complicated. Here you have got a random process Xn, you want to design an FIR filter, so called optimal filter, maybe you can denote the coefficients at W0 to Wp, so that the output Yn, it becomes a very good estimate of some unknown signal Dn, some target is called desired response or target signal Dn. That means, if you take the error, what we do, this error, as you can see, it is Dn minus Yn, and Yn depends not only on Xn, depends on the filter coefficients you choose. So, if you take mod of E square n, that is the variance of En, and all processes are assumed to be stationary here, then mod square of En will be a quadratic function of W0 to Wp. So, you minimize them. Quadratic functions have got one unique minima and maxima. In this case, obviously it will be minima, okay, because you can only reach minima, you cannot, I mean, there is no maxima here, because you can always deviate from your optimal coefficients and get more and more error variance here. So, so find out for which coefficients the mean square value of this output error En is minimized. So, that will give rise to the optimal filter, that is unique, and that is also called FIR Wiener filter, okay, not in the name of the great mathematician and statistician Norbert Wiener. Okay. So, what I do, we can first, and I am assuming for the time being that all the processes and all the coefficients, everything is real valued. Okay, this can be generalized further to the case of complex valued case, but that I will do only later. I might not rederive it for the complex valued case, I will just quote some reference, okay, but I will give you the results. So, here what I mean is this, what is En? En is Dn minus Yn, and what is Yn? Yn I can write as W vector transpose Xn vector, where W vector is this coefficients, Xn vector is called a regressor vector, you can easily see W transpose Xn is what? W0 Xn plus W1 Xn minus 1 plus dot 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 Wp into Xn minus p, which is the convolution actually between Xn and this W sequence, and that gives you Yn. Okay. So, what you have to do, if you take mod En square, take its expected value of mod En square. Now, you know, this will be, this is clearly, this will be a quadratic function of W's, because after all Dn minus W transpose Xn, it contains all this W0 Xn, W1 Xn minus 1 dot dot dot. If you conjugate the entire thing, there is no question of conjugation of course, because we are doing real valued case. If you just square it up, you will have terms like W0 square, W1 square, W2 square, and W0 W1, W2 W3 like that. So, it is a quadratic expression in terms of W0 W1 W3. Any quadratic expression like this has got a unique minima or maxima. In your case, it would be minima. You can also verify by second derivative. Nevertheless, so we have to find out the derivative equated to 0, okay, and that will give rise to the best filter. We will follow that approach little later, but we can derive the same filter purely from orthogonality point of view. That is, if we orthogonally project, for if I want to minimize this, that means minimize this means what? Minimize the error. Which error? Dn minus a linear combination of what? Xn dot 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 up to Xn minus p, right? Square of that. That is, we have to find out, we consider the space, subspace spanned by Xn minus 1 up to Xn minus p. We have to find out an optimum linear combination. So, that is, we have to find out a particular vector in that vector space, so that the error between Dn, that is the external fellow Dn, and that vector, that error has minimum norm square. Norm square is same as variance here, okay, because inner product with itself, which is just variance. That means we have to basically do orthogonal projection of dn on the space spanned by xn to xn minus p. Thus, we can show that this projection is unique, it exists, and that projection is such that dn minus that projection, that vector, that error vector will have the minimum norm, that is minimum variance. So, this minimization of E of mod en square amounts to orthogonal projection of dn on the space spanned by xn to xn minus p. Okay. So, we can just find out that projection and get this expression for that Wiener filter. Okay. That is a standard way, straightforward way. We will also do this direct minimization, because that will take us to what I want to conclude this course with, that is a case of adaptive filters. Okay. So, this linear combination is some coefficient, say w 0 times x n, then w 1 times x n minus 1 dot 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 up to w p x n minus p, their summation. There is a coefficient. This error must be orthogonal to, that is d n minus this must be orthogonal to whom? X star may be n minus I. This should be equal to 0 for I equal to 0 1 dot 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 up to p. Okay. You can do it in a systematic way, either you can do it in the laboratory or in a very smart way. What do you do? You can expand this equation, you will get E of d n into x star n minus 1, that is a cross correlation between d n and x n with lag I, and you can take this product between this summation and x star n minus y, there will be, you will have correlation values of x in that equation. So, first you put I equal to 0, then I equal to 1, you get separate equations, but you can put the equations in a matrix vector form easily. What I do is, if this be the case, then I generalize this as, this part remains as it is, d n minus w transpose x n, x is a column vector, w transpose is a row vector. These times, if I put this way, this is a scalar, d n minus w transpose x n is just a scalar. If I put this way, if you take its product, if you multiply by x n star, that also should be 0. If you multiply by x n minus 1 star, that also should be 0, because of that orthogonality. If you go up finally up to x n minus p and star and this product, again that should be equal to 0. But what is this vector? This is x n vector again. Okay. Again, by habit I am putting star, but actually there is no scope of star here. So, you can as well erase the star, because I mean I have assumed every process to be real here. So, forget about this. Okay. Those things come in the complex case, they are, you have to just generalize the derivations, which I will not do, but I will give the results. Just to make life simple, everywhere it is treated to be real. In this case, okay, I will just do little manipulation. This is a scalar number. So, it does not matter whether I put on the left hand side or right hand side, scalar times a vector or vector times the scalar, either it is same, because scalar times a vector means the scalar number multiplies each entry of the vector. So, whether you put it on the left hand side or right hand side does not matter, I put on the right hand side, and also w transpose x n is same as, this is same as x transpose n w. A transpose B and B transpose A, when A and B are vectors, they are same. So I just substitute W transpose X by X transpose W, X transpose N W, and take this entire scalar factor to the right hand side. So that means what I get is X n vector multiplied by this is equal to a 0 vector, all vector which all of length p plus 1 where all the elements are 0. Now, if you carry out the product, what you get first term is x n vector times d n. So, d n, what does d n do? D n is a scalar, desired response, d n into x n, d n into x n minus 1, d n into x n minus 2 dot 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 d n into x n minus p. So, what I get? We get a cross correlation between the process d n and x n. Cross correlation is lag 0, lag 1, lag 2, lag 3, and because of stationarity that becomes independent of n, because x n and d n are assumed to be jointly WSS. So, what you get is a cross correlation vector p, I will define p separately, okay, minus x n x transpose n E of that, or maybe here only I define. Okay. This is what comes from the orthogonality. What is x n d n? Just for your sake I am elaborating it here, otherwise I could have directly written, just to avoid confusion in the first instance of the treatment. This is so d n into x n cross correlation with lag 0, d n into x n minus 1 cross correlation with lag 1, finally up to lag p. Okay. This I denote as some vector. Usually the notation in the book that is used, actually notation uses p, but I have already used a p here as the order. So, what I do, maybe I put capital P. This is a vector, mind you, capital P, cross correlation vector. What is x n into x transpose n? That will give rise to actually correlation matrix. X transpose n is x n, it becomes a row vector. Okay. If you do that x n into x n, expected value of that r 0. Okay. Then x n into x n minus 1, expected value r 1, dot 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 up to r p. Again x n minus 1 to x n, expected value of that lag is 1, so r 1. So what you get is something like this, r 0, r 1 dot 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 r p. Stop this matrix and symmetric now. Something like this, and this is called R, input correlation matrix. So, this is P vector, this is R matrix. Suppose these are known to us, these statistical things, and because of stationarity n disappears, and suppose P vector and R, information about them is available to us. Then you have a simple equation R W equal to P, and you get the filter as W equal to R inverse P. That is the Wiener filter expression. And we put a cap here to indicate optimal filter Wiener filter, that is R inverse P. This comes from the orthogonality. Okay. So, if R is known, P is known, then we put that. But there is another way of deriving, that is by computing, by differentiating that error variance directly with respect to each tap weight and equating to 0. We do that because of some other reason, because that gives rise to that can be used further to develop what is called adaptive filter. That is, you can write down epsilon square as, that was what was E n? E n was d n minus W transpose x n. okay, and no point in putting mod in this case. So, I am still carrying out the notions of complex case, but they are not required E square n. And what is E n? D n minus W transpose x n. This square of that, but instead of square I can always write this into this, that is a scalar number, say a square can be written as a into a. Further, any scalar number a and its transpose, they are same, a and its transpose are same. So, I write this as this d n minus W transpose x n into its transpose, because both are scalar. So, transpose of a scalar is itself. Now, if we expand E of d n, that is d square n, that will give rise to the variance of the process d n, it is a stationary process. So, sigma d square independent of n. Then one cross term is W transpose E of x n d n. E of x n d n we know, this is equal to what? P vector. Actually, I chose the order of the filter to be small p. I should have used some other letter, maybe L or K or whatever, because this cross correlation vector p being a vector should have been denoted as lowercase p. But since I have already used the p, the letter p, lowercase p somewhere, I am carrying on with capital P, that actually it is a vector. So, W transpose p, another cross term is W transpose x n d n, again W transpose p, because x n into d n, its expected value is p. So, twice this, and the last one is W transpose x n and transpose of W transpose x n. Now, transpose of W transpose x n is what? X transpose n first, then W. So, W transpose x n transpose W. W is not random. So, E will work only on x n into x n transpose, which is R matrix, correlation matrix. So, what you get is W transpose R W. This is the expression. You can see this W transpose P, this is linear. It has only first order terms of the weights. If you put W as a vector, rho, it becomes a row vector here. You will get only first order terms of each type weight. But W transpose R W will consist of the square terms, second order terms. This I have to derive. That is, I want to make it this way for k equal to 0 up to p. I define a notation del with respect to W of epsilon square. It is nothing, I just put the partial derivatives in a vector form. Okay. This must be equal to zeros, it is called 0 vector. Okay. So, erase this, I have given you the meaning of del W. Should be 0 vector. Now, W transpose P, now firstly del W sigma d square, it is independent of the filter weight. So, that will give rise to 0, this will give rise to 0 vector. If you differentiate this quantity sigma d square with respect to each type weight, each derivative is 0, then W transpose P. What is W transpose P? This is W 0, say P 1, P 0, 0th entry, W 1, P 1, dot dot dot, W P, P small p. If you differentiate this with respect to W k, a particular term, what will you get is P k. If you differentiate this, what is happening? If you differentiate this, say with respect to W k, only the kth term will be picked up, that has only W k, others do not. So, W k P k, so that will give rise to P k. So, if you put back the derivatives, partial derivatives in a vector form, that is del W 1, del W 2, del W 3, what will you get is P 1, P 2, dot dot dot, say P 0, dot 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 up to P small p. That is equal to your P vector. So, that means this will give rise to minus twice p vector. Complicated is here. What will this give rise to? So, here let us remember the terms. Let me write down entire thing on top. We have got minus 2p plus this del w of this quantity w transpose r w, this must be equal to 0 vector. Okay, sigma d square I am forgetting because there is already giving rise to zeros. Okay. So, w transpose r w, and R is a symmetric matrix. What is r w transpose r w? What is r w firstly? This is r. Consider the ith row. What is the ith row? Ith row of this times this, that will get multiplied by wi, wi times I equal to 0 to p. There is this w transpose vector. If you take its ith entry wi, that will multiply what? After you take this r w vector, you can call it w prime, ith entry of w prime, isn't it? So, ith entry of w, just a minute. If you call that matrix R w, R is a matrix, W is a vector, so R w is a vector. If you call that vector, give it any name, okay, so X or say Z, then W transpose Z means this Z I, and what is Z I? Ith row of R times W vector. What is ith row of R? R I j W j, j will vary from 0 to p. So, replace that here. Okay. All right. Now, you see, suppose you want to derive it with respect to w k, you want to derive this quantity with respect to w k for a particular k. What I will be doing in this outer sum, I will be first separate out the k case w k, that is I equal to 0 to p, in that range when I equal to k, I becomes equal to k, that case I am separating out. And then w I equal to 0 to p, but I not equal to k, this. Okay. Okay. I have to differentiate it with respect to w k. First, consider the second term. In the second term, in the outer summation, w k never comes. For each I, because I equal to k has been separated out, but for each I in the outer summation, in the inner summation, w k comes once when j becomes k. So, I get r I k w k, and there if I differentiate with respect to w k, I get r I k. So, this gives rise to w I r I k, simple, I equal to 0 to p and I not equal to k. This term here outer also have got w k on the outside, and inside also j becomes k and then you have got w k. So, it is a product. So, first you differentiate with respect to w k, hold this inner summation as it is. It is a differentiation of a product. So, that will give you and then hold outer one w k as it is, differentiate inner quantity the summation with respect to w k. So, you get only one term r I k w k, that is differentiated, you get r I k. So, R I k and outside you have got W k. So, R I k W k. Okay. Now, consider this second sum. Here I equal to 0 to p, but I equal to k was not included. I equal to k case means W k R k k. Okay, that will be here. Actually, I made one. Just a minute. Well, I made one mistake actually. When I took out, separated out I equal to k case, I equal to 0 to p was here and I equal to k was separated out. So, this time I cannot put as any independent I is already k, isn't it? I varies from 0 to p, out of which I equal to k was separated out. So, in this left hand side wherever I had I is to be replaced by k. So, actually it is not R I k, it is R k k. Now, you see the right hand side summation I have got W I R I k, I equal to 0 to p, but I equal to k is excluded. If I is equal to k is included, I would have got one more term. What is that? W k k R k k, and that is what I am getting here. So, that means this term can be included there, and I can simply remove this constraint. Okay. And now you see again this is R k because I equal to k case was separated out. So, these corrections should be done here also. This is k. As I told you, I equal to 0 to p was here, but I equal to k was separated out. So, whatever I separated out there I was to be replaced by k. So, I did not do that. So, here again I replace I by k. These are corrections to be done. Now, consider the two summations R k j and R I k. Firstly, permit me to replace j by I here, does not matter. So, it becomes R k I W I, that summation over I, and R k I because of symmetry is R I k because R is symmetric. Okay. That means what I have here, I can write as again W I R I k, and that is what I have here. So, twice W I R I k, I from 0 to p. Okay. In fact, instead of R I k, I would prefer the previous other one, R I k equal to R k I. Why not put R k I? So, since I am minimizing this derivative, now what is this R k I? What does it mean? I differentiated that quantity where from it came actually. It came from deriving this. With respect to W k, but I am deriving this with respect to W 0, W 1 up to W p. So, k can take value from 0, 1 dot dot dot. What is this summation? You can easily see if you take the R matrix kth row R k 0, R k 1, R k 0, R k 1 dot 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 R k p and W 0, W 1 dot 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 W p. This row times this column multiplied by 2, of course. This is what you get to obtain the derivative, the kth derivative. And now k can, if when k is 0, you get the first row, then second row, like that. So, this is very simply this is the R matrix, isn't it? This is R matrix easily. So, what you get is twice R W. That means del twice R W. So, that means if we sum up What is the net gradient? We earlier had minus twice p. In today's class, I kept it uppercase. In the next class, I'll convert it into small p. I will change that small p from the order. I used the letter small p to denote the order of the filter. That I will change to some other index, because let us stick to the convention followed universally. Nevertheless, 2p, and here I got twice RW. Remember, this is the gradient expression. I will use it in the adaptive filter. This gradient should be 0 when I have got the minima. That obviously will give rise to the same Wiener filter. You can see W cap equal to R inverse P. Okay, this is the optimal filter. In practice, if you know R and P, fine, you can calculate this R inverse P. But problem is R and P are not always known. R and P are not always known. In that case, you have to supply information, this information externally. Okay. What I do, this actually gives rise to the interesting case of adaptive filter. When R and P are not known, or when the input statistics or the joint statistics between Dn and Xn they change from time to time, you cannot have one filter designed once for all. So, what you should have? You should try to have some adaptive mechanism by which your filter learns from the data that is coming in and tries to adjust itself by some iterative method, so that finally it converges on what should be the corresponding Wiener filter for a given R and given P. Then again, after a while, if R and P changes, then again that adaptive mechanism will be used. It will further read from the data and readjust itself, so that you get a new R and new P, and you get another corresponding Wiener filter. So, there will be continuous adaptation mechanism. If input R and P changes, it will track, and it will have an iterative self adjustment procedure, and it will finally converge. Every time that iterative procedure should converge at the corresponding Wiener filter. There are plenty of adaptive filter algorithms, but most celebrated is that least mean square algorithm, which we will be just considering in the next class, and I will just give one or two applications, like channel equalization in communication and all that. Okay, that will end this course. Thank you very much. Okay. What we have seen in the previous class in a nutshell was this. We are considering a filtering, optimal filtering problem like this. There was a random process Xn. It was passed through a FIR filter W0 dot 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 WP. Instead of P, as I told you, I will be changing it to some other thing now, because I am using P as a vector for some other context. So, W0 to say WL. So, L plus 1 coefficients. Output is Yn. There is a desired response Dn. The error is, so you try to minimize the mod square of this error, okay, with respect to the filter taps, because this E of, in fact, you can call it epsilon square, is independent of n because of stationarity. This quantity you have seen is a quadratic function of W0 dot 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 up to WL. We have also found out two things. One is, if we calculate the optimal filter directly, W cap is R inverse P, where R is E xn transpose, P is E xn dn. Okay. Other thing you have seen, the gradient. This in the morning you have seen for a particular W it was twice R W minus P vector. This you have seen. Now, one thing is that you can find out the optimal filter directly by R inverse P, but suppose you do not want to follow this path, suppose you do not know how to compute the inverse of a matrix. We can propose an alternative method, which is iterative method from defined directions, and I want to receive only one and I do not want to hear others. So, I will be adjusting my antenna weights, so that a beam is formed, that is antenna gain is maximized in only one direction, the direction in which I want to hear, and nulls are created in other directions from which other signals are coming. So, thereby we do some kind of special filtering. Now, here the persons who are receiving the transmission signals, they are in motion. So, their direction changes. So, this business of giving null in certain directions and applying beam in certain directions, this needs to be again adaptively adjusted. Okay. So, that gives rise to adaptive beamformer. So, there are many applications which we will find in this book. So, I will not discuss them any further. I hope you enjoyed this course. Now, in a probability and random process, there are too many things in this. So, obviously, in a UG course like this, all cannot be covered. But I suggest, I feel that whatever has been covered will serve as a good background, and you can now go into more advanced topics. Okay. For instance, you can go into topics like martingales, you can go into topics like queuing theory and things like that. These are all given in at an introductory level in Papolis's book, and the background that is required for the reading those, for the studying those, that has already been covered. Okay. So, I hope you enjoyed this course, and for any feedback you can contact me, you can write to me or you can contact me. Okay. It will be nice to have a communication with your end. So, you can contact me here. My email address is mritun@ece.iitkgp.ernet.in. Okay. My phone numbers 03222283512, that is office, 283513, that is residence. Okay, then hope you enjoyed this course, and in case you learned something from this, that will be a good reward for me. So, thank you very much for all your attention. Good luck and goodbye.